give a hand for our next speaker.
Thank you. Hello, my name is Max Harley. I'm going to be talking about the art of shellcoding. Shellcoding is truly a dying art. People these days sort of tend to gravitate, newer people that come to security kind of gravitate towards web exploits because it's much more approachable than like running through binaries, kind of scary stuff. So most people don't really get to experience shellcoding or binary exploitation. So in this talk, I'm going to try to prove that shellcoding isn't as hard as people make it out to be, and it's also still extremely useful. So a little bit about myself. I really enjoy CTFs. That's actually how I got on this topic. That also means I don't do this for a living, so don't take anything I say as fact, but sort of use it to formulate your own strategies for shellcoding. So if you want to follow along, you can go to presentation.maxh.io/shellcode. You can bring it up. It has really good mobile support. This is actually the master presentation, so if you, it'll like follow me throughout this presentation. Kind of cool if you want to do that. So in this presentation, we're going to learn how this string of totally random looking characters becomes this. And as a security researcher, we really like this because this means we have a shell. We get a root shell, we can run whatever we want, and that's pretty awesome. So a quick question, is anyone here a C developer or like part-time C developer? Sweet, we have one. It's more than I thought there'd be, 2. And does anyone like CTFs? Everyone, yay. So these are the groups that this is really going to be extremely applicable to. So for developers, obviously teaching like secure programming practices. But for CTFs, if you look at all the DEF CON qualifiers, there's always at least a little bit of shellcode that's required in every problem. So kind of a cool thing. I keep throwing this term around, but what is shellcoding really? Very generally and very typically, we refer to shellcoding as assembly instructions that allow us to run arbitrary code, typically in like a C or C++ program. So things built in C++ are like servers, even games a lot of the time are built in C or C++. So that's really where you're going to be able to use this. Why is shellcoding relevant? This is kind of a big one because a lot of the times we look at web exploits and we kind of disregard binaries. But Dirty Cow came out recently. That was really topical. And it actually, this specific version that I have linked here uses shellcoding to generate a root shell on whatever device you run it on, which is really bad. So it uses this tool called MSF Venom to generate the payload, but it's still shellcode and it's still cool. If you look at any of the Metasploit modules, they all, to get their shell, use shellcoding. And you also get like hacker style points because shellcoding is kind of crazy, kind of cool. So definitely hacker points, you get those. So we need to learn a couple of things before we start actually shellcoding. I'm not going to spend too much time on this, but I'm kind of going to overview it. The first thing, very seemingly obvious, but it gives a good perspective on what we're going to be talking about. We have a couple definitions, vulnerability and exploit. Vulnerability, I'm just going to define it, a flaw in a system that leaves it open to attack, and an exploit, an attack on a computer system, especially one that takes advantage of a particular vulnerability. So we see exploit takes advantage of a vulnerability to do malicious stuff. So for people who do web app pen testing, cross-site scripting is your vulnerability, and then session hijacking is your exploit. Very similarly, in binary exploitation, our buffer overflow, which we'll talk about in a second, is our vulnerability, and getting a shell, some sort of shell through shellcoding is our exploit. So buffer overflow in 10 minutes. This is a preface, kind of what you have to know beforehand. I'm going to try to keep it down to 10 minutes. But buffer overflow is extremely practical. We see it's good for training people, good for tutorials and stuff. And it's also extremely practical. So a lot of newer developers, especially ones who are programming in C, tend to kind of fall into this trap of allowing buffer overflow vulnerability to be used. So here we go. First thing we need to know, assembly. This is the lowest level language that can reasonably be programmed in. So actually C is converted into assembly. So if you program C code, it gets converted to assembly. We have these things called registers. So these are the things that are highlighted in red. EAX, EBX, there's an ECX, ESP. There's a ton of different names for these. And we have a couple simple commands. MOV moves data. So on the first line, we move the number 5 into EAX. Second line, we move 10 into EBX. The third line, just like in whatever language is your favorite, the plus operator will add two things. In this case, add adds EAX and EBX and actually stores it into EAX. So we get 15. So we add EAX, EBX, 5 plus 10, 15. And then we print. One specific register I want to talk about is EIP. EIP is our instruction pointer. This one is really necessary to understand how the buffer overflow vulnerability works. EIP holds memory locations, and it also tells the program where to go next. I'm going to get into a kind of a demo to show you, help you understand this. So I have this C program. So we start off in main. We create an integer called 5, or an integer called A, set it equal to 5. We have an integer called B, set it equal to 9. We say A is equal to A plus B. We call a function, and then we print. So we print hello world, and then a new line, and then 14, because A is equal to 5 plus 9. And that's it. So we'll compile this, run our program, and we see we get hello world and 14. 14. So we're going to use a tool called objdump. What objdump will do is take our C program and convert it to assembly. This is going to help us understand how C kind of converts to assembly. So you don't need to understand all of this right now, but we can see some things that look familiar, like these numbers over here, 5 and 9. Actually, maybe easier with a mouse. So you can see 5 and 9 over here getting placed into areas. We see add. We're adding two things. We call new function, like we saw in the C program. So it calls blah, 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 FB. If we scroll up, we can see this function, blah, 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 FB. And all this does is print something. The rest of it is kind of unnecessary. So the first column over here on the side, these are the locations. So these are the locations of where we are. The second column is the processor, what's called opcodes. And this is what your processor actually reads. Or these are the values that your processor reads. And then this last column just converts the opcodes into sort of a more human-readable something so that we can understand it. So next, so how is data stored in assembly? So we need to think about how we can interpret this, how some sort of compiler will convert our C code into assembly. And it actually, so we start off, we arrive at main, so we need to do something with main. We create an integer, and then we create another integer, and then we exit. So in assembly, there's actually an internal stack that's used and kind of created. And we push and pop things from the stack to tell us where we are, what kind of values are being inserted. So in this piece of code, this is how the stack would look. So we first push the main return address at the bottom of the stack. And then we push the variable A, then we push the variable B. And that's kind of how it's built. If we lay the stack out horizontally, we can see that we start off with the topmost part, and we kind of go on from there. We're A equals 4, and then the return address for main. So functions on the stack, it sort of operates a little bit differently, kind of weird how functions work. So we start off, we're in main, we create the return address. We first push the return address for main, and then we create the integer foo, set it equal to 2. Then we call new function. When new function is called, we push the return address onto the stack so we know where to come back to, which is kind of important because if we didn't know where to come back to, the program would just kind of keep executing and nothing good happens from that. So next we push things onto the stack, bar and then the variable name. And then this function exits, so we return back to the return pointer, come back, and those things that were on the stack got pushed off because we left this function. So that's kind of how functions work on the stack, this internal stack that assembly uses. So now that we have sort of that prerequisite knowledge, how do we exploit this buffer overflow vulnerability? So if we can figure out a way to overwrite the return address and figure out where EIP is going to execute from that return address, we can actually control the execution process. So for example, if we write more characters into some sort of buffer, so actually I'll get to that in a second. So here we have source for some program we made. We first create a function called new func. We create a buffer, and then we use gets. So gets is a function in C that allows us to get from standard input and then store whatever we get into a buffer. The only problem with gets is that it allows us to put in however many characters we want. So it doesn't have this restriction of our buffer being only 5 characters long. We can put whatever we want. So in this stack, we see that if we were to input hello into standard input, we would have a stack that looks like this. We first push the return address for main. That's this 1, 0 down here. That's this one. And then we go to the new func. We see that we store the return address for new func. And then we create a variable A called hello, or that has the value hello, 5 characters long. It works out perfectly. The only problem is if we put in some sort of character that is longer than 5 characters, we completely overwrite that value that was once there. In this example, we're overwriting 08042B, which is the second thing in the stack, with 080484, because we push greater than 5 characters onto this buffer. So that means we're actually able to control program execution just by writing more characters than what's allowed. So this is really important for C developers because they need to make sure that no one is writing more characters than what your buffer size is. So I'm going to do a little demo. As I said, I really enjoy CTFs, and this was a really good example of, let's see. So this was a really good example I found on one of the CTFs I did of a, let's see if we can make that smaller. Oh, there we go, that works better. So this is a really good visual representation of what we're going to be, what I'm actually talking about. We have this source right here. So we see we go to main, we take one of the arguments, and we pass it into the vuln function. We create a character array called buff that's only 16 characters long. And then we use strcopy, which just copies whatever we write to it, or copies our input into that buffer. The only thing, just like gets, strcopy will not check for bounds. So this means we're allowed to write however many characters we want into this function. So here's what our actual stack looks like. So we have our buffer. That's a 4x4, so it's 16 characters. We have 8 characters right here of sort of null space. And then we have EBP, which is pushed. Don't really need to know about that. But then we have EIP. So eventually we are actually able to, if we write enough characters, you can see, I'll put it into ASCII mode. If we write enough characters, we can actually start writing values into EIP. So that's definitely a problem. But we can see this really cool function over here called giveShell, which actually gives us a /bin/sh shell. It's telling me how to do it. I don't need that. So let's look at what we have. So I'm going to check out the make file. So this is saying it's going to copy, or it's going to compile that overflow2.c file that we just looked at. Name it overflow2. obj dump. So we're going to use the obj dump tool that we just talked about, and find out where the location for that giveShell function is, so that we can hopefully call it. So we can see we get a memory address over here, 0408 AD. So I'm quickly gonna show you that this works really well. Uh, 84. And we can see in this saved EIP, this green space up here, I just have written the 080484 AD address in this. So if we run it, it runs. It prints this out, adds our location, and then we get a flag. Yay! CTFs are fun. That was pretty cool. So that's a really basic buffer overflow vulnerability. It really takes advantage of overflowing some sort of buffer to allow us to execute wherever we want to. The last thing I'm going to talk about is Linux system calls. These are really important for learning how to shellcode because a lot of the time we'll need to call kernel functions or things in the kernel to allow us to do cool stuff. So in assembly, the int 0x80 is just means let's call something in the kernel. So you set up your registers, you call int 80, and then it executes whatever system call you tell it to. So specifically, we're going to be talking about system call 1. And syscall 1 is the exit syscall. So anytime a program exits, you actually have to call something in the kernel to tell it to exit the program cleanly. So I'll actually show an example of this. So we start off. This is just a way that we can program in assembly. We move 1 into EAX, so we are using system call 1. We move 0 into EBX. This just means that we're going to be returning 0. In C, this is a kind of a way to say this program exited cleanly. And then we use this call int 0x80. So exits already. So we created a binary off of that called exit. And if we run exit, it exits. So how cool is that? We were able to exit our program. So we can actually use this. I don't know if you guys can see that. But this is just saying it says 0 over here, and that just means that it returns 0. So it did exactly what we told it to. We'll get a little bit more complicated here and use system call 4. System call 4 is write. So this system call 4 will tell your kernel to write to whatever buffer you want it to write to. So we'll start off up here, say create a string called message, MSG. We allocate it. We say we want it to say hello world, and then 10, which is just a new line operator. We get down into the code. We use system call 4. We move 4 into EAX just to denote we're using system call 4. We move 1 into EBX. That just means we're going to write to standard output. You can specify buffers, so if you want to write into a buffer, you can do that. In ECX, we put the pointer to the message, which we declared above. EDX, we put how many characters we're going to write. We're going to write 12 characters. And then we call int 80. So that's going to execute that. Next, we exit the program like you would, like our previous example showed. So I'll make this and run it. And we see we get hello world. And if we echo this, we return 0. So again, it did exactly what we wanted it to. And everything went perfectly. Great. Yay. Cool. So now for the actual shellcoding. How are we going to insert our code? This is a good question. So calling arbitrary functions is pretty cool, but we really want to get shell. That's kind of really what we want. So here what we're going to do, we're going to go back to our previous example. So instead of A's, we have this kind of long string of A's. Instead of A's, what we can do is actually insert the opcodes that we saw when we did the disassembly. So if we insert opcodes here, and then we set EIP, so we overflow into EIP and set EIP to the beginning of our buffer, our program won't know the difference between the stack, or the calls that it's trying to make, and our buffer. So it'll actually start executing what we say in our buffer. So for this presentation, there are actually tools to mitigate this, where the program will know if the stack or it'll know the difference between the stack and our shellcode body, but I won't really get into that. So if I can get to, here we go. So if we were to insert, instead of those A's, if we were to insert that middle column, the B801000, and then point it to the beginning of that, it'll actually execute exactly that. So making shellcode, typically, I say typically, pretty much always, we'll write our shellcode in assembly. We'll use what's a tool called NASM to compile our assembly, and then use objdump, which is the tool we talked about, to disassemble the binary that we just wrote to figure out the opcodes that we want. The reason why we don't use something like GCC or any sort of other compiler is because GCC does like really spooky stuff because the code is so optimized that typically you won't really know what you're feeding into the buffer or feeding into the shellcode stack. GCC is optimized for speed and not size, so we typically really just don't want to use that. This leads us into making good shellcode, which is very different from making shellcode. So good shellcode is kind of what denotes or shows the difference between like hackers and security researchers. Hackers will try to get the shellcode as small as they can, sort of as a game. I mean, if you've ever seen people play code golf, it's kind of the same thing. Smaller is better. And the reason for this is because if we have smaller shellcode, we can fit that the same code into a smaller buffer. So if some programmer gives us a buffer size of like 30 versus like 525, we need to make more efficient shellcode to mitigate or to use that buffer. The next thing, shellcode cannot use two zeros next to each other. And the reason for this is because strings in C are terminated by this character. So if we have a string, it'll kind of just shut the string off and kind of cut it where it is. It's just kind of a rule that you have to have because of C. So I'm actually going to do an example. So this is going to look really familiar to you. We just did this. This is our old exit shellcode, or our old exit assembly. We move 1 into EAX, we move 0 into EBX, and we call int 80. When we do objdump, we can see how many characters is this. We have 1, 2, 3, 4, 5, 10, we have 12. This is 12 characters long. So I also wrote a new one that does a little bit of magic. We start off by XORing EAX with itself. What this will do, if you've ever done like binary operations, XOR puts a 0 in something that's the same. So if you XOR something with itself, it's just going to set it to 0. And then we increment EAX by 1. And I'll show you why we do this. And then for EBX, we XOR EBX with EBX, so that EBX is set to 0. And then we call int 80. So this is extremely helpful. Because look at how much smaller our shellcode is now. We went from 12 characters to 1, 2, 3, 4, 5, 6, 7. From 12 characters to 7 characters, just because we didn't have these kind of crazy amounts of zeros here. So we can see that the easiest way is not always going to be the most efficient way to do this. So now we want to insert our shellcode. So we insert our shellcode into the buffer. We point the EIP to the beginning of our buffer. Magic happens, and then we get a shell. So that's pretty sweet. So I did have a demo of this, but I left my lab stuff on a USB 4 hours away, so that sucks. But here's a really good representation of it. So we have our this very familiar code now. We call getInput. We create a character array of size 80, and then we call gets on that buffer. So we have this kind of 80 character long place that we can throw stuff into. If we assume that 0xb776 is the beginning of our buffer, we can insert the shellcode that we previously wrote, the new exit function, to the beginning of that buffer. And then we write a ton of A's, or just whatever kind of we have. We write a ton of A's, and then we overwrite EIP to set it to the beginning of that buffer. In this case, B7676. And so what'll happen is it gets, obviously this would be cooler if I could show you, but it would go to the top, it would do gets, we overwrite it, and then it just exits and exits cleanly, and nothing even happens. Kind of pretty cool. So here's a few tricks. There's a lot of tricks to shellcoding. Again, it's kind of an art. You're trying to make it as small and as kind of cool as you can get it. So there's a couple tricks actually for shellcoding and for kind of exploiting buffer overflows in general that are really extremely helpful. Our first one is the nop sled. So nop is a really cool command, a really cool assembly thing. It stands for no op. It's 0x, or it's x90, so it's hex 90. And all it does is nothing, which is the beautiful thing about it. All it'll do is increment EIP by 1 and do literally nothing. So why is this useful? The problem with this is that when we overwrite EIP, we need to set it exactly equal to the beginning of our shellcode. We need to set it to 0xb776. And if we don't set it to that exact address, it'll do whatever it wants. It'll just kind of flail around, have no idea what it's doing. But if we put no ops before the shellcode, and then have our shellcode at the very end, then this gives us a much larger region to kind of put our stuff into. So we start off our nop sled. So here we start off, instead of all these A's, we replace it with a nop sled. So we can set our EIP to anywhere between B776 and the end of our blank space before EIP, and it will nop, find our shellcode and execute it. That's extremely useful because it's really hard to figure out where the beginning of our buffer is. So this gives us a lot of room. There's also another, not really a trick, but another kind of tool we have available to us is MSF Venom, sort of in the same tools packages as Metasploit. And it'll generate shellcode for us. It's not a trick or a tool really in assembly, but it'll help you do your research or whatever you want to, whatever you're doing it for, because you don't have to go through the process of writing an exec VE to like /bin/sh to generate your shell. While it's a good thing to know how to do that, we do have tools that will do it for us. And it'll even do things like nopsled for you. So you just tell it to like the shellcode that you want to generate, how big your buffer is, and then if you want a nopsled or not. And it'll generate that whole string for you, so you don't have to really do anything. Now the thing, yeah, so that's definitely good to have. So the last thing is recommended reading. So this is you can get very deep into this. There's a lot to it. So definitely reading and practicing are the easiest ways to get better at it. Shellcoder's Handbook is a super great book that sort of steps you through the buffer overflow, shows you how to exploit it to get a shell, shows you how to set GUID to 0 to get a root shell, which is pretty awesome. Talks about other vulnerabilities other than buffer overflow. Really just cool stuff. Next, ASM tutorial. If you want to generate your own shellcode, learning ASM assembly is going to be how you do that. So if you can write it really efficiently, you'll get better shellcode. That's just how it's going to work. And then learning about binary exploitation. Honestly, this link isn't even about binary exploitation. It's more about CTFs. I'm going to find, whatever, I'll just type in. CTFtime.org. CTFtime has lists of all CTFs that are coming up. Honestly, this is going to be the best way to practice is by finding out whatever CTF is coming up next and just doing it, because doing it is going to be how you learn. You can read a lot, but doing it is going to be how you get better. I would definitely recommend checking out CTF Time. Recommend participating in as many as you can, because you will benefit greatly from this. So thank you for listening. If you need to contact me, here are some avenues to do that. And that's it. Does anyone have any questions?
Yes.
Chris.
So optimization, right? So shellcode, you want to shrink it down and make it as small as possible.
Yes.
So when you're obfuscating shellcode, sometimes these shortcuts can cause issues. Have you had any experience with that?
I have never needed to obfuscate shellcode.
Well, let me ask you this. Why would you want to obfuscate shellcode? Maybe that's something people want to hear about.
Okay, yeah. So shellcode obfuscation, it'd be useful, I mean, I guess for like
evasion of detection, right?
Yeah, I mean, yeah, detecting like there's programs that will check like if malicious code is being run. So if you can actually obfuscate that, then you'll bypass a lot of that.
Right.
So
those standard ends, right?
Yeah.
Normally they would say that's a malicious function, but you would obfuscate shellcode.
Yeah, if you were,
you could get it, trick the system into performing a function that normally would say, hey,
yeah,
this is off limits. Right?
Yeah.
So sometimes the same command, even obfuscated, can give
yeah.
results.
So that's actually a very good point. If you want to just write shellcode, writing it smallest is going to be best. If you want to write shellcode that'll bypass a firewall or whatever antivirus, you're going to want to obfuscate it. Pretty much it. Yeah, pros and cons of different things. Hey, what's up?
So, do the same, I'm assuming that this is all for like x86 architecture, right?
Yeah,
So,
yeah.
do the same principles apply if you're like, attacking like an ARM Cortex or something?
Yeah. So if you were to, you need to find some way to compile your ARM. But yeah, if you were trying to exploit an ARM system, exact same way you write your ARM shellcode. do your obj dump or whatever your tool of preference is, and then throw that shellcode up. Yeah, exactly the same way. You just have to use a different compiler.
Yeah, be
Yeah.
aware of your big endian versus lately endian.
Yeah.
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 You may accidentally
Yeah.
try to access something outside of memory space and completely break a device.
Yeah.
ARM's not very
Especially with ARM. Yeah. 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 Hey.
So two things, RPI Sec actually has, on GitHub research, RPI Sec,
Mhm.
they have a binary exploitation course that you can go through. It has all the slides, and resource file information, and walk you through a lot of that.
Yeah.
Same thing is Shellcode, but I know that it's, the second version is pretty old. It's from, do you think it's still relevant, or have you?
Yeah, I mean, there's definitely some stuff that's, if you're gonna do the labs on it, you need to actually download an old version of like Red Hat or something, because there's a lot of new, things like stack canaries, things like ASLR, are newer ways of evading like shell coding attempts. So there's definitely, it dates it a bit, but the shellcoding handbook does explain a lot of like these new, at the time, newer technologies, like bypassing ASLR, bypassing stack canaries, so that you actually do get, it still works, but using all of your resources. So looking at that book is going to be good, but using doing CTFs is going to show you how to sort of modern day, or how we do it 5 years from when that book was written. Hey.
Question about address space layout randomization.
Yeah.
Do you have to disable that in order to do any of this testing? Or
Yeah, so
with
the
that in place?
yeah, so the lab that I had set up, actually I had disabled ASLR in the kernel, because you have to do some kind of more advanced techniques to bypass ASLR.
But it's possible.
But yeah, you can bypass, just disable it if you don't want to have to deal with it. Yeah. Hey.
Religious question. What debugger what do you use for debugging disassembly?
Actually, I really prefer Radar 2. It's a really awesome tool, and it can do a lot of, it's kind of meant for this kind of stuff, like binary exploitation. So I would definitely recommend Radar 2, recommend checking out that tool. But obj dump works. You can do some awk stuff to get it to actually output the shellcode you want. But Radar 2 is definitely a good tool to check out for debugging. Yeah. Any other questions? Hey.
Which do you find more difficult to deal with, ASLR or stack canaries? Or is it kind of just dependent?
I mean, it's there's a process to how you bypass each one of them. So I mean, after you learn the process, I mean, they're both. It's just a process, yeah, to doing that. Chris.
Is that a dinosaur in your shirt, or what is that?
So that's a lizard. It's a gangster lizard who's actually in space.
All right.
Yeah. Yeah. Mind blowing.
Good job, Max.
Thank you very much.
Thank you.